All right, I hope everybody had a good weekend. So I'm still kind of behind on grading. I did grade your midterms, so that was like the only thing I did accomplish. So I did put in those grades. For the most part, they were pretty decent. There were a few uh, lower scores. So I think I'm going to offer a retesting or, like corrections, I mean. So corrections up to 70%. So then calculating it, because you know me, I can't just do my exams out of 100. I think it was out of 105 this time officially, so times zero point 0.7. So you have to get over a 73.5, and that's what you can correct up to. So if you scored over that, right, don't worry about it. And some people, like I said, did pretty well. And then if you were under this, right, I'll give back exams at least today, so you can have those. And then if you're below, right, you can test up to the 73. And then let's talk about the field trip. So field trip is already next week. So we'll talk about the field trip and then the alternative assignments. So we'll do kind of some options. So let's talk about alternative assignments for people. If you can't make it out there, I know it's a long day, potentially, especially with the driving for the Medford people. And so if you can't make it out there, so here are the alternative assignments. And there's going to be two alternative assignments, so you have kind of options. And so the first alternative assignment, I call it the no travel option. And so on Blackboard, I've opened up some resources as well. So that under the information tab, there's, I think, links to like, we had to do a virtual field trip one year because of COVID. So there's all these different links you can kind of read about the caves. So that's one way to get some information. And so for the no travel option, I'll ask for 2 short essays. So like 1 page, single spaced. And so we'll do 1 essay on the Oregon caves. If I could spell, geez. And then another short essay on another geologically relevant site, and ideally like locally. So if I could spell geologically relevant. So I was thinking the table rocks would be another good topic. I'd also be open to, isn't there like the fish hatchery? I still haven't made it out there. Or somebody went out to, what was it, John Day, right? So John Day, you could write about that so you don't have to travel out there. So anything kind of local that's relevant, or, the mountains. So that's the first alternative assignment, no travel option. And then I made a second alternative assignment, and I'll call this the light travel. And so if you can visit a site, so, like visit the Table Rocks, or anywhere else, again, that's kind of relevant. Two Vale Park, right? You could look at the history of that and talk about the river, anything. I'm pretty open. But just take a selfie, and then you can just write 1 essay about that site that you visited. So that's why I suggested Two Vale as another local site. So trying to give equal workloads. So either no travel, 2 essays, again, 1 on the Oregon caves, 1 on something else that's cool, or visit somewhere, Table Rocks, Two Vale, I don't know, Cantrell, Buckley. What else is cool that's nearby? Any of the lakes, right? Applegate Lake. And then one essay on that topic. And so then let's just look at the caves and some information. So like I said, I posted some information. I forgot to print this, so I will print this out hopefully during your break. It's just kind of some pre-lab questions to get us in the mind frame of the cave and maybe looking at some background information. And then this is some information about the caves, because there are some rules and stuff to think about. Well, okay, so we discussed travel time. I don't know why their website keeps, it says it's 2.5 hours from Medford. I don't remember it taking that long. Yeah, I feel like 1.5 hours, maybe like 2 hours. But we'll still do meeting time at 11:30 officially so that everybody has plenty of time. And so this might be slightly outdated. So I haven't had this issue where the GPS, and just be cognizant, right? So it says that the GPS sometimes takes you through the forest route. Let me see if I have. Here's the Google Maps. And so right now it automatically picked what I would call like the best route, and that you go through Grants Pass and then Cave Junction, right, kind of all the way around and then to the caves, versus it's saying don't take this back road. So you can see how it's kind of highlighted. So that would be technically the shortest distance, but I think it's all back service road, so you probably don't want to go that way. So like I said, just watch your GPS that you're sticking on the main road all the way around. That's the better way. But yeah, I still think it just takes 2 hours, maybe 1.5 if you're speeding. No, don't speed. And then they do say that it might take like 30 minutes from about Cave Junction or so, or that last mile post that it says. So just go slowly on the last 10 miles. It's pretty windy if you've never been there before. And then they do say that if you have an electric vehicle that they don't have a charging station, so just make sure you have plenty of charge or plan your charge appropriately. Although none of those vehicles like plan your trip for you, right? Like, hey, I need a charge up here. Pretty fancy now. And then some things to remember for the cave tour. So it is cold in the cave. So they say it's about 44, so it is pretty cold. Most people just brought like a sweater or something, and that was fairly sufficient. And then wear good shoes, of course. But then they do say, where's our safety tip? So it says, do not wear shoes that you have worn previously in another cave. So they want to, of course, stop the spread of this white nose fungus. So that's fatal to the bats. So again, just make sure you have not hiked in caves with these shoes before. So good shoes, warm clothing. Bring a camera, or have your cell phone somewhere safe. And then what not to bring, and they will make you put up your stuff, so they will not let you cart around stuff in the caves. So they have flashlights, so don't bring flashlights. And then you cannot have backpacks. They didn't say water bottles, but they will not let you bring water bottles like on the trip, right? So bring your snacks and stuff before. So that would be my suggestion, right? Get there early, drink food, drink water, eat food. And then they have bathrooms there. But then, like I said, you can't bring anything with you. So either leave it in the car, or they do have lockers that I think you can rent out and store your backpacks there. But yeah, there's nothing like crazy, obviously, like no crawling, but you may have to like crouch a little. Some of us, not so much, but other tall people, right, might have to do some crouching, so they don't want you to have things that could harm the cave, of course. And then, I mean, I don't think anyone's bringing their pet, but yeah, leave your pet behind. So I don't think we have service animals in here. Otherwise, I'm not. You would want to check about that because, yeah, they don't want pets or anything. Does that sound good? Questions? So, okay, cave trip. So again, it's already next week on Tuesday. So just plan. And we'll say 11:30 start time, at least for the official tour. So I would try to get there by 11, so you have, like I said, plenty of buffer time and no one's trying to drive up the mountain really quickly. We don't want anyone flying off the mountain. I'll wear a sweater, clean shoes. Does that make sense? And then, yeah, I think officially we were not approved for guests, but I'm still maybe going to try to appeal. It's a little awkward. That's not in line with practice or previous trips. So previous trips, like I mentioned, we've had people's moms and grandma and significant others, and it hasn't been an issue. So the official word is no. It is a public space. So I can't necessarily control everything. So that's what I'll say on that. But yeah, I may try to appeal officially still. Other questions, comments? All right, let's, I think, move on. Oh, one tiny little reminder thing. So lab this week, we're doing our one pot reaction. So we did some shuffling around. So should be a fun reaction though. And then we do have potentially, I think they said they were going to come in today for pictures. And so of course, if you don't want to be in the pictures, let the camera people know so you could like go stand somewhere and they're not like trying to shoot you. And if you definitely want to be in the pictures, I'm sure they'll have waivers for you to sign and make sure you look your prettiest for that. And then no lab next week. I think that's goes without saying with the caves, but we can do makeups next Thursday. So that's another good time for makeups if there's some stragglers on that. All right. Don't think I'm missing anything other than, I was thinking probably no quiz this week. Part of that is just selfishly I want to catch up on grading, but I didn't necessarily want to quiz us again since we had our midterm. But if you guys really want a quiz, we can certainly have one. See some votes for no. I mean, I don't know. Or if we want to just like a practice quiz for practice and not a grade. So maybe we'll do that, just kind of a practice ungraded quiz. All right, so let's go start 25 now. So now 25 just kind of goes off of 24, I feel, right? So we looked at our kind of reduction potentials, redox reactions, and so now we're putting them kind of together in this cell potential, which reminds me, somebody sent me like some crazy video of like this battery that lasts forever, and then I didn't have a chance to like watch it, but it was kind of one of those semi-conspiracy videos, but I definitely wanted to check it out since it's relevant to our chapter here. Yeah, well, that's what I wanted to see is like how long can these batteries last? And, well, how much potential energy is in them? And so that's kind of the first part that we have in our book here. And so it just tells us that the difference in potential energy between our anode and our cathode is our cell potential. And so we can kind of think of that, right? So that's our difference in voltage. And so that kind of gives you, right, your kind of waterfall, your pushing force of, right, what direction will those electrons go? And again, we've kind of gotten a taste of this, but now we're going to put our half reactions together, right? And that'll tell us whether they're going to be spontaneous or non-spontaneous. And, you know, the other way to phrase it here is that they have our cell potential depends on the relative ease with which our oxidizing agent is reduced and our reducing agent is oxidized. But again, it's more about kind of pairing our overall reactions. And these are good things to keep in mind, but I think it tends to be a little confusing when they say these things, and I just care more about, like, what's our reaction and which way we're going. Yeah?
Does it have more potential if it's easier for it to deoxidize and reduce or less?
So it depends which way it's going, right? So if you have your reducing agent, right? So yeah, if your reducing agent wants to be reduced and it's at the anode, then yeah, it's going to be more favorable. But that's why I always say, like, it's better just to kind of keep track of, like, your reaction and then add the potentials. And then that, like I said, gives us just, like, our numerical sense there. Oh, I think I started in the wrong spot. So let's start here. Sorry. I don't know why I started over there. So our electrochemistry, the book starts us off with kind of our simplest battery. So going back to battery conspiracies. This is just our coin cell. So you could do the same thing. Maybe you've done this before, where you've lined up a bunch of pennies and then put some sort of electrolyte solution through them. And then you get, again, a cell potential. So again, there's our voltage, that is essentially our pressure, or again, our waterfall that's going to push our electrons through our loop here. And so then we're kind of given this formula in this book, U, which really this is our energy, right? So potential energy is really what we want to define that as. But they have, okay, so variable U, which in this case is just our electrical energy. And so that's equal to our volt times our charge. And so again, right, our voltage is our potential. And so then we have to figure out, well, what is our charge? And so our charge is basically equal to how many electrons are coming by. And so let's define what a coulomb is. And so we have that an electron is 1.602 times 10 to the negative 19 coulombs. But of course, we know that we tend to work in moles. And so that's where our Faraday's constant comes into play. So Faraday's constant then for a mole is 96,485 coulombs per mole then. All right, so then if we go back to our charge in our joule here. So, okay, so then that's just our unit. So our joule then is equal to our volt times our coulomb. And then, right, our rate. So basically our Z. So how much charge is going to be equal to our current. So I. So our current times our time there. And then current is usually measured in amps here. So we have our amps. And an amp is defined as a coulomb per second there. So that's where, Okay, so times time, seconds, so then that gives us, right, coulombs then for our overall charge. And so now let's look at how we'll apply this whole relationship together. And so there's just, again, a summary of our units. But you have kind of your typical problem that's set up like so. So a current of 1.5 amps flows for 5 minutes. And so what is the quantity of charge? And basically just asking, right, total coulombs. So take a second to think about it and plug it in, right, going back to your kind of units here. I'm not sure I was going to actually. All these physicists in here getting excited.
It's just nostalgic for me because at my high school, I took the very first ever electronics class they offered, and CHEM was a huge part of it.
Oh, nice. So did you talk about like resistance of different materials or?
A little bit, but we also mostly talked about building circuits with series and parallel, and how all of that different math would work out. But so obviously it started with Ohm's law because we're talking about resistance in regards to series or parallel circuits with different resistors or loads. Yeah, fun times.
So then let's go over this one. And so it's really just a unit conversion issue, right? So we have 1.5 amps. And then again, we said this amp was equal to our coulomb per second. And so we basically just need to convert 5 minutes to seconds and figure out how many total coulombs that was. So times 5 minutes. But then I need to get rid of minutes and get seconds. So seconds on top. And then cancel, cancel. So amp times my second. So then that gives me coulombs. And so what do we get for our total number of coulombs? So 450. Oh, forgot to do times 5. That sounds good. So questions on that one? And so yeah, to address your point, we will not talk about coulombs or Ohm's law. Sorry, we won't talk about Ohm's law, but we should at least kind of think in the back of our mind of like what Ohm's law is telling us and the natural resistance of materials. So that's why we use like copper wiring, or you could also use like silver has a pretty low natural resistance as well. So just thinking about those properties, right, and what makes something then a metal and conductive. But yeah, we won't get onto that kind of engineering side in this chapter. We're more focused on the potential there. And so like we've seen from our lab then, electrochemistry is either the study of our redox reactions that produce or require an electrical current. So again, just like we saw in lab, right, we could make a reaction happen by producing an electrical current, right, some sort of water splitting too. That's been proposed as another way to make hydrogen and oxygen and the energy uses of that. Or looking at, so right, the demo that I did 2 weeks ago, I guess now. So that was showing our electrochemical cell, so essentially a battery. Again, thinking about our voltage really is kind of the focus. So how much potential do we have for work here? And of course, that's just our conversion between our chemical energy, right, our reaction, and then it does the redox reaction to give you electrical energy, right, so current flowing. And so then, of course, we'll get to this part of quantifying things as spontaneous or non-spontaneous, but I think we're kind of hinting at it already, but any spontaneous redox reaction, so it would be a positive voltage, but like I said, we'll get there. And so that would be your voltaic cell or your battery, essentially. And so again, right, that's what gives your battery power. And then going back to battery design, it's just a question of, is that reaction then easily reversible so that you can charge your battery back up, right? You apply current, and then non-spontaneous reaction occurs. And so that's right, the bottom part is, okay, well then we can have our non-spontaneous reaction, so negative voltage, right, negative potential, so we'll get there. And of course we can make it occur by, again, applying electrical energy. So either how we make sodium metal or fluorine gas, so that's dangerous, or again, water splitting. So any of those non-spontaneous reactions. And so then we want to be able to draw out our battery and kind of understand our cell here. So this is, again, this is the demo that I did, but this is a pretty common spontaneous reaction. We've both seen it in like the single replacement form, right? If we put it in a jar together, which it is showing here. So it's showing, so you wouldn't set up a battery like this, but all that this is proving is, yes, this is from our single replacement reaction. So right is spontaneous, so you guys can kind of go back to the activity series with this one. And just saying, okay, our zinc is able to donate electrons and then spit out our copper metal. And I do like this little diagram. So again, it's showing us in solution, so not split up as a cell. So this is, again, inappropriate for our battery, but just we want to see our flow of electrons here. So again, our zinc solid, and then it, right, reduces, so gives up its electrons. So then copper, bloop, plucks them up, and then, right, or, yeah, so it's oxidizes, sorry, I'm trying to say that it does a reduction in that, right, yeah, it's the reducing agent. I should have been more clear. Yeah. So reducing agent, so it does a reduction, but yeah, is oxidized, sorry. Yeah, essentially. So then giving up our electrons, and then, like I said, copper plucking them off, and then causing it to come out on the surface like we've seen. So again, that's just our spontaneous single replacement reaction. And so if you remember the demo, all the galvanic cell is it took this spontaneous reaction and then we split them up and made a circuit out of it. And then of course, right, we can potentially quantify these things. We'll also look at other scenarios of like how much electrical current you would need to, like, let's just say plate out copper wire or copper. So we'll look at some, like I said, examples. And then again, redox reactions involved our movement of electrons. So again, that's why we're going to split them into two cells. And so again, like we've seen, it has our potentials. So going back to our difference in voltage to generate an electrical current. And so we'll see the math on this, but just kind of tying everything together. Obviously, a spontaneous reaction does not require external energy. So then we would have a negative delta G. So we'll have a formula for that coming. And again, our voltaic cell is our battery. And so it can produce an electrical current. And so it makes that caveat here. So to use that current, right, we have to separate the place where oxidation is occurring from the place where reduction is occurring. So that's why we make our little half cells. Or if we were to get into like battery design, so they do have like small separate chambers and they'll have they're like electrolyte paste material, right, separating the two redox reactions so you can get this current going. Man, that reminds me, I was watching some video, but now I need to try to find it because they were like analyzing the batteries. And now I forgot like what was supposed to be taller, the anode or the cathode. But basically they could tell battery quality by like, I forgot how they were x-raying them and seeing like how uniform it was. I'll try to find that video. It was pretty cool so I could share it. I totally forgot to save it for today. All right, so once again, our half reactions are kept in separate half cells. So if you can think back to the demo, and we can always, take these materials out again if people want to like go electrical engineer on me. But right, that's what the little beakers were for. And we'll draw it out in a second. So we have our beakers, and then again, right, we have to complete the circuit. And so that's what I was doing with the demo. So like I said, we'll practice drawing it out. But our electrons, of course, flow through a wire. So those were what our alligator clips were for. And then we had to have, again, ions, right, our electrolyte, to have the movement of electrons. And so that's why I had that salt bridge, which if you remember, I used a pretty makeshift one of a cheesecloth that was soaked in a sodium chloride solution. But it could be anything. If you were making like a fancier salt bridge, you can look online. There's like recipes for agar bridges. But yeah, I've used those in the past, only temporarily, because you can imagine those are not very stable to try to get those to work. They kind of fall apart. But yeah, the cheesecloth works pretty well. You can also, any way you can fashion a salt bridge. But basically, again, complete circuit. Yeah. It probably could to some extent. So like obviously you don't want it to be too low, but then you do have to like take into account like the common ion effect, and that could potentially like push the equilibrium and like help it ideally. So I think that's what happened in the case. Was it your like potassium iodide, if I remember correctly? Could have been like really close in potentials, but part of like Le Chatelet's principle, and like your ions in solution, we're supposed to favor like the iodine formation, but yeah, and it probably does have some effect, but we probably like won't quite get into all the math, and you might see something a little later where you're like, okay, there could be some effect, but yeah. This is always good to do in like practice too. I found echem is a little tricky. And so then with the setup that we did with the demo, so we had our electrode. So our electrode was our metal, if it is a metal, right? So like I said, we were doing zinc and copper in the demo, and so that would be fine as our electrode. Or if you have another solution, so basically like an iodine, I forget what iodate solution. So if you have something like this or other redox reactions, I think like the sulfate one, so you have the issue where you don't have like a metal, right? Like you can't just take solid iodine, obviously, and like clip it. That's not going to work. And so for those, you use a separate electrode, so either a graphite electrode like we did in class, or sometimes you see these like glassy carbon electrodes. Maybe like platinum could be used sometimes as an electrode. And so you'd want to draw that on an exam. So let's say I gave you a redox reaction and there's no metal, you're trying to draw the circuit. Well, make sure you put your electrode in there. And so graphite, glassy carbon, platinum, all those would be appropriate. And then so other things to remember. So our anode is where oxidation occurs. So you can kind of remember, and they're both vowels. And then it should be connected to the positive end of the battery in our electrolytic cell, and then loses weight in our electrolytic cell. The cathode is where reduction occurs, so just remember that. And then cations are attracted to it. Should be the negative end of the battery, and then gains weight in electroplating. All right, so we want to practice drawing out, so we'll kind of redraw out this voltaic cell here. And so we just want to practice doing that. So I'll just kind of copy it. And well, let's write out our reaction. And so again, we're just going to practice with our zinc copper cell. And we could start off by just writing our reactions out. So again, zinc, and then zinc is going to, again, supply the electrons, so undergo oxidation. But we'll verify this in just a little bit, right? That this is the correct direction. You know, we kind of know it. We could go to the activity series, right? See that zinc is higher on the activity series, so therefore it should be, again, supplying the electrons. But we want to just verify that with our reduction potential. And I think that'll be clear once we have the reduction potentials. Plus 2 electrons. Okay. And then you at least want to make sure that our electrons are balanced. So, okay, 2 and 2. And then I just want to, again, redraw this voltaic cell so we can practice drawing it. So we want 1 half reaction. And, I mean, you all know I'm not a good artist. You guys can go fancier on your beakers, but just trying to show, okay, we have 1 cell. I'll put my zinc on this side. So ideally we want the anode, just kind of for convention's sake. So anode on our left side here. So again, zinc supplying our electrons. And then we want to label it. Okay, here's my zinc metal. So again, it's a metal. We can use it. Then we need our counter ion. So they did tell us it was zinc nitrate, but really any zinc soluble 2+ solution would work. So I'll just put zinc 2+. So I'll put zinc nitrate in parentheses, but anything else, I can't remember if zinc chloride is soluble. But any sort of soluble zinc 2+ ion will work. And then we have, right, alligator clips going from zinc. And then you could either put this to a light bulb, or I also put voltmeter, since that's what we did in class. So again, either we're going to light something up. The only tricky thing with the lights, of course, is right then you get into a what's the voltage needed to actually turn on this light. And there's a chance that you could still be getting current but not hit the correct voltage, right, for your little light bulb. So the voltmeter may be more reliable. So again, completing our circuit. And so then it's going to go to copper metal here. So right, our strip of copper dipped in our copper bath. So copper 2+ ions in solution. Let's see what they pick. So again, a nitrate, probably for solubility, but again, another copper 2+ solution would work. And then the last bit, right, some sort of salt bridge. So just have some ions floating. All right, so that looks good. And then we want to just put in our flow of our electrons. So again, zinc is producing the electrons. And so then they're going to be flowing all around. And again, right, going to copper here, so that copper can then deposit more copper onto our metal there. So those are all the parts that we need. Again, right, we need our 2 electrodes. In this case, we were able to just use the metal. Otherwise, we would have had to pick glassy carbon. Electron flow, salt bridge, complete circuit there. So that looks good. All right, so this is just kind of, again, re-emphasizing what we've been doing. So again, our voltage kind of gives us what we need to drive our electrons through. And then again, reminding us what our current is. And 1 amp, but again, you probably want to use Faraday's constant. But all right, so now let's go and figure out our cell potential, right? So we had said it was our difference in potential energy between our anode and our cathode. And so I was looking for, there it is, our table of standard reduction potentials. And so now let's take our little cell that we've drawn. So going back to our cell here. And I said, well, let's figure out, if this is truly spontaneous. And so let's look up our reduction potentials, but let's do it for our reactions, right, in the correct order. Because we'll go through the notes, we'll see what the textbook says and kind of these helpful hints, but like I said, I think I find them more confusing as opposed to just kind of adding up our reduction potentials. So let's find zinc. So now we look at zinc. And so then it's down at the bottom here. And it's going in the wrong direction than we want it to be, right? So we're having zinc supply the electrons. So we'll flip the sign, so that gives us positive 0.76 volts. So I'll just write that over here, so positive 0.76 volts. Now let's look up copper. And so making sure that we get the 2 electrons. So here it is. So copper 2 plus 2 electrons. And so that has a positive reduction potential at 0.34. And so then we can add this up. I think we did this, like I said, for our demo, but just so that we're all reminded. And so if everything is the same concentration, which we'll get into the concentration bit, like I said, at the end of the chapter. But basically, we would expect this to be spontaneous, so it's positive, right? So positive 1.1 volts. So that means, right, that's how much energy that it has. So it is confirming what we've drawn here, that like, yes, it is going to make a battery. It's going to be spontaneous. It's positive. So how we have it drawn is correct, right? So if you were to kind of technically try to do the opposite, right, where it's like, well, what if I wanted copper to be the anode? Well, you could flip the reaction, and we could do that now. But you would see that formally, right, that that's not going to work. So just, we'll say, what about the opposite? So if we just flip the reactions, and so now that gives us, right, negative 0.34 volts for that one, and then flipping our zinc. So that's now negative 0.76 volts. So this overall process is negative 1.10 volts, right? And so again, that's just saying, okay, well, the opposite reaction is not spontaneous. You could force this to go possibly, right, if you pass electrical current through it, and then it might go the opposite way, and then we'd start plating out zinc. But again, it's just telling us under normal conditions, right, the copper is not going to be doing this. So it's not going to be supplying our electrons or anything. So this would be not spontaneous. But like I said, we'll relate it to delta G a little later. All right, that's probably a good point for a break. So we'll come back and, like I said, we'll keep calculating our cell potentials. All right. Any questions come up during the break? And so I did print out our lab assignment, we'll call it in quotes, for the Oregon Caves. If you're going, you can grab it over there, grab it on your way out. So like I said, it's just the pre-lab questions, and then you'll write a short little essay about the caves and how much fun you had. All right, so kind of continuing with our idea of cell potential here. So when we calculate these and just look at all our cell potentials, these are typically under our standard conditions. So about 25 degrees Celsius, 1 ATM for gases, which I don't think we'll run into. But this is kind of, I think, going back to a few questions that have been asked. So this is kind of where this gets addressed in this, typically for 1 molar concentration of the solution. What we're going to see, and what I've kind of hinted at, is that we just need the concentrations to be the same. But we'll look at a formula that addresses like kind of how to treat it when the concentrations are different, because that does affect the cell potential. We're not really going to get too deep into it in this class, but just kind of for your knowledge, or kind of going back to the battery demo, that's what I was doing. I didn't grab 1 molar solutions necessarily, I just grabbed roughly the same molar solutions. And then again, we'll sum them. So that's my favorite way to do it, is we'll just sum our cell potentials for our half reactions, again going in the appropriate direction, based off of our reaction. And then just re-emphasizing some points. So again, when you draw out your voltaic cell, the whole point is that you want your anode on the left side. So again, your anode is oxidized, so it's giving the electrons, right? And so again, flow of electrons through your voltaic cell, and then cathode. So reduction is occurring. So again, it's taking those electrons. So we see our flow there. And then, so these are, again, more kind of helpful hints. So again, our anode is our metal that's oxidized, so typically speaking. So again, it's supplying those electrons, so whatever helpful hints you need. And then our cathode is made up of our same metal that is produced. So again, typically speaking, so I'll put kind of zinc versus our copper scenario. And then again, just a reminder about if we run a redox reaction, and we can look at more examples. So again, looking at our reduction potentials. What's a good one? So like chlorine, right? So, I mean, you wouldn't use chlorine. Bromine, but any of these solutions, or the iodate, that's the other one I brought up. Or even this like manganese oxide to manganese 2+, right? There's not a good solid for that, so you probably still want a sacrificial electrode for this reaction there. Or water splitting, right? Again, we'll need some sort of electrode. Or this one, this other manganese reaction, right? Aqueous species to aqueous species definitely need a separate electrode. And so again, that's what they mean by the inert electrode, which we identified as either, right, graphite, glassy carbon, platinum. Those are kind of the main ones. And so again, our inert electrode does not participate in the reaction, again, just like our pencil, but just provides a surface for the transfer of those electrons. And okay, so not only do we need to be able to draw out our cell, but we also should be familiar with this little cell diagram here. So this is called our cell notation. And then this is going to show us our special case, so where we require an inert electrode. So let's break down what's going on in this reaction, maybe calculate some cell potentials. And so let's look at this. Maybe we should verify that this reaction is going to occur. So, right, let's look at our reduction potentials. And so we have, right, just kind of setting up our scenario, so looking at what's going on. So we have our oxidation reaction, so it looks like our iron is our reducing agent, right? So it's supplying the electrons. So let's look at that reduction potential. So iron to iron 2 plus, so let's just check that out. Iron to iron 2 plus, so again, making sure you pick the appropriate one. Again, right, kind of thinking back to your activity series, so you have iron 3, which is almost close to 0 for the reduction potential, versus this iron 2, which is, well, negative 0.45 in this direction, but we're going the other direction, so positive 45. And then versus our other half reaction. And so they have it drawn out for us. And so again, we're noticing a few things about this setup. So we're going from manganese, so let's calculate that. So 7 plus to 2 plus. So 5 electrons. So let's find that process to get the reduction potential. Again, making sure that I picked the correct one. Where is it? Wrong one. Hopefully I have it here. There it is. All right, so then which direction are we going? We're going in this direction, so that looks appropriate. So our manganate species plus 5 electrons gives us N2 plus, so 1.51 volts there. And now I forgot what it was, plus 1.51. Okay, good. And so I just wanted to verify that, yes, this cell was written in the correct direction. So plus 0.45 plus 1.51. Yeah. Not for this part, no. So yeah, we can just take our reduction potentials here. And okay, so then we should have positive 1.96 volts. So okay, that's good. And then, so let's look at our notation. So what it's telling us. So again, how it should be properly written for our voltaic cell is, so we have on our left side, right, our anode. So again, where our oxidation is occurring. And then notice the order that it's written in. So what kind of helps you is your metals should kind of flank your outside. And so we start with our metal, and then we have, right, our counter ion, so 2 plus ion. And again, that's our anode side. And then notice they're separated with just a single line. Then we have our double line here, so basically saying, right, this is another cell. Then we have all our species here. So this is a little maybe a little different than some of our other ones. So then we have all our aqueous species. So starting with our reactants, products, right? Acidic conditions, so just kind of showing that we needed our acid in there. And then single line to show the separation. And then do not forget your electrode. So this is where this one's a little tricky. So just to kind of abbreviate, again, what your cell diagram should look like in this form is you have your oxidation reaction, right? Metal, metal ion, double bar, and then your reduction reaction, which should be your cathode, and then again, metal ion and metal. So see if you can do that. Let's just practice. Let's go back to this voltaic cell. So just write it out right now in the proper notation. So if I need to scroll around. And so again, we want it in this kind of shorthand cell notation. And again, you want to be able to either take your voltaic cell and write the shorthand notation, or take the shorthand notation and draw out a pretty battery diagram. So yeah, take a few minutes, write out what would our shorthand be for this cell diagram. And so let's just draw it out together. And so again, it should just be zinc, single bar, zinc 2 plus, then double bar, copper 2 plus, single bar, copper there. And you could also put in, zinc nitrate, copper nitrate. I'm not going to be that picky, so either way. As long as we're clear that, again, it doesn't have to be nitrate specifically, just as long as it's a soluble 2 plus ion. Yeah. Oh, sorry. Oh, that's just the platinum, remember? Our platinum electrode. Yeah, so that's why they picked platinum, but again, right, you could have picked glassy carbon or some graphite. But yeah, they just picked the platinum electrode there. All right, a bit of background, and again, I think I kind of mentioned this before, but we have to have some sort of standard to kind of measure these. Just thought of something on a side here. So this is a really good paper if you wanted to get into eChem at all. And so this is kind of like what the process looks like. And I'm kind of curious what this correction is. I'll have to look at that later. But basically, Gillian Dempsey is a really great professor over at, I think she's at UN Chapel Hill or UNC Chapel Hill. But she and her group wrote this really good paper that's, well, you can see it. It's a practical beginner's guide to CV. And it just kind of gives you an idea of what you're trying to do. And you're trying to see if these electrical processes are reversible. And that's, again, part of how you measure your reduction potential. Bless you. And so you have, I mean, I'll let you kind of look at this article if you want to. But basically, they call it is you want this like duck wave. And then where you have your peak is where your reduction potential is. And so this is where this comes into, right? So again, we have to have a standard. So you're doing your little duck waves. And well, you know, the equipment could be slightly off, so you always have to have a reference. And so they also have assigned, again, one of our half reactions to 0. And so this is our reduction of H plus to H2. And so that's just defined as 0, right? So that's our standard hydrogen electrode is what that is called. And so again, that's just kind of like our standard. And then I think I've kind of mentioned that a lot of time you use ferrocene, for example, in like inorganic chemistry. So that's what, see, it mentions here. So ferrocenium and ferrocene, so that's also generally used as kind of a standard to help calibrate your little duck machine here, which is, again, basically what you're going to be doing. I was trying to see if they had a better ferrocene wave. Well, anyways, we can dive into that paper. But okay, so that's where our cell potentials come from. And so again, they're all compared to this standard hydrogen electrode. And so again, all we're saying that half reactions with a stronger tendency towards reduction than our standard hydrogen electrode have a positive value. And then half reactions with a stronger tendency towards oxidation have, again, a negative value compared. And then like we've seen, we can flip the sign, right? That's all that this is telling us. That, okay, if we need to go in the other direction, we flip the sign of our reaction. And then, so then we have our cell potential here. And so this is what I don't necessarily like about your book. And so the way they present it, they always present it kind of in one direction. So notice, right, they give you the voltage of the opposite direction. So if we look at that again, so right, they have the anode, so zinc going to zinc 2 plus, but then they wrote negative 0.76 volts. So if we go back, and so negative 0.76 volts is for this direction, right? And so I don't like how they treat it, because basically what they say is like, okay, you have your standard reduction potentials, and then you can take your difference of cathode minus anode, which is why they left it in the negative form. Now, to me, that's super confusing. Like, I do not understand it. I mean, I do, but I'm always like, am I doing the right thing? So I think it's better to, like I said, you just flip your half reaction. So we would have gone here. It should be. Oh, thank you. Nice. But yeah, so we would go to this table or page, again, 949, thank you, in our book. And so we would see that we want to go the opposite direction. So again, I would flip that reaction, flip that sign, and then I would just formally add them together. So I don't like how the book does it of like take the difference between them. It's essentially the same thing, but like I said, I think it's more confusing. And then again, we want to show which way they're going to flow. So that's kind of the whole point I make in flipping our zinc copper one is we're saying, well, it's not going to go from the copper to the zinc, right? That's not spontaneous. But really we're kind of verifying which direction our electrons will flow. And so they should flow from the anode to the cathode, again, once you pair those half reactions appropriately. Does that make sense? And we can rewrite this one, right? So I would kind of rewrite it if we were writing out this reaction. And I would flip our signs here. So zinc gives us zinc 2 plus 2 electrons. And that's positive 76 volts. This should be 0, right? Because I said that's our standard hydrogen electrode. We can verify it. So yes, right, H2 plus 1, excuse me, H plus 2 electrons give us H2. So going back to here, okay, that's the direction we're going. It is at 0. But again, just kind of verifying, yes, it should flow in this direction. Again, zinc is acting as our anode, just verifying that positive potential there. And so then this is just kind of verifying this. Again, I think it's easier to see once we write out the reduction potentials, because otherwise then you're just kind of comparing overall oxidation potentials. So then they're just kind of comparing. So zinc has our stronger tendency to oxidize, and so then therefore, right, it would be the anode. So that's another way to look at it. But like I said, I think adding the half reactions is the clearest way. So I'll highlight that. So again, comparing, right, our two oxidation reactions. And then, right, they give us some general trends. Again, that our redox reaction will be spontaneous when there is a strong tendency for the oxidizing agent to be reduced and the reducing agent to be oxidized. But, right, I would just, again, say add up our half reactions. And that really verifies, you know, again, will it happen? Is it spontaneous? Or are we going to need to perform some electrolysis? And then, okay, so higher on the table, and then the stronger tendency to be reduced. So I think we kind of have seen that. But again, just kind of re-emphasizing. So we have our oxidizing agents on top, like fluorine. So anything that wants to get reduced versus our reducing agents on bottom here. And then the activity series would probably look flipped, right? So all these would be at the top of your activity series. So lithium, calcium, sodium, right? That should all be at the top, probably not in the same order, again, because now we're actually looking at redox potentials versus just reactivity, but kind of just comparing those two lists there. Does that make sense to everybody? So again, just add those half reactions. Then you won't be trying to memorize all these kind of sayings. And so then now we're getting into our G. And so again, like we've kind of emphasized and overemphasized in this chapter, a spontaneous reaction will take place. And okay, so they have it laid out when a reduction half is paired with an oxidation half lower on the table. I mean, that's kind of confusing. But again, we could take our zinc and copper scenario. So here's zinc. Where's my copper? Here's copper. So right, zinc is lower on the table. But again, I find that confusing to think about. So I'll just probably make my point again of add half reactions, right? If this all doesn't make sense, just add your half reactions. And then once we add our half reactions, like we've been seeing, well, if our voltage is positive, then it's spontaneous. And like I said, eventually I'll give you a formula of what our delta G will be. And then again, delta G will be negative. And then when our cell potential is negative, then that reaction will be non-spontaneous. And delta G, typo there, will be positive. So again, looking at this, we could tell that, again, this is paired lower. So this is going to be functioning as our anode to, again, I just like rewriting it. That's the easiest way to see it. So again, giving us this positive reduction potential. All right, so then we'll practice our cell potentials. And so we don't need to multiply our half cell values by our amounts to balance our redox. So do not multiply half cell values. And so again, the way that your book presents it and calculates it is that it's the cathode minus the anode. So this works, but again, I'll put just add your half reactions. So same thing. So now just go ahead and practice that. So we've already done it, but let's do it again. And so let's see if we can figure out our cell potential for this reaction. And again, you can tell me if it is spontaneous as written or if it's non-spontaneous. And so tell me what you found. So again, I would write our separate half reactions. So aluminum solid gives us aluminum 3 plus 3 electrons. And so what was the reduction potential you found for that? Oh, sorry. flip to the chart too. So where is it? So down towards the bottom, right? Which, if we're going by the other hints and tricks in the book, well, that sounds like a good start for our anode down here. So did we find, well, it's written as negative 1.66, but again, I'm going to flip it, right? Because we're doing the reverse reaction of aluminum giving up electrons. So 1.66 volts versus, so let's find our other half reaction here. So nitrate plus 4 hydrogens gives us NO and 2 waters. And so where on our reduction potential is that? Okay, so this is nitrate, 4H plus, 3 electrons, NO, 2 waters. Okay, so 0.96 volts. So that looks good. And then let's add them to get our cell potential. And again, right, it's going to be positive at least, so that's a good sign. And so we should have a cell potential of 2.62 volts there. Did we all get that? Does that make sense? Question?
Oxidizing agents, we only flip the sign for, sorry, do we only flip the signs for the oxidizing agents?
Yes,
The table.
or the reducing agent, right?
Okay.
But that's why I'm always like, just add the half reactions, right? Because we're just looking at our reaction here. So we're saying, okay, we're starting with aluminum solid, we're ending with aluminum 3 plus, and then I just like copy the equation, right, and determine do I need to flip it or not, right? So again, going back to this one, well, it's written in aluminum 3 plus 3 electrons, but we're doing the reverse. So then that's how I know, okay, well, I'm going to flip the sign on that. Does that make sense? But yeah, that's why I like just flipping the reaction appropriately, then trying to remember, okay, it's cathode minus anode, which, I mean, some people might be fine just remembering the formula, but I like making sure we're going in the correct direction. And so, again, I think we've kind of emphasized the same point. We have a practice problem, and so their goal is to do it without calculating the cell potential, but I mean, again, I really don't like doing that since it can be kind of more confusing. But take some time to do it maybe both ways mentally in your brain. Maybe try it. Can you predict if A is going to be spontaneous or non-spontaneous by the little tricks? Is that completely useless to you? Do you want to just calculate the E cell? Because that's my instinct is like, well, I just want to get this cell potential anyways, just so I can be sure. But kind of practice this out. See what you get. And then, well, yeah, we'll figure out which one is spontaneous, and then we can draw out our little cell diagram. But yeah, take some moments. How can you figure out which is which? What works for your brain? So what have we found and kind of what ways work best for y'all? So let's look at A first. And so what do we think about how it's written? Spontaneous, non-spontaneous? What were some clues? Any? Yeah, what'd you find? So non-spontaneous. So how did you get there? So good. So that's one way to do it is if you can identify the tricks. Yeah, exactly. And then, so for me, I do like plugging in the reduction potential, so I'll still calculate it out. So, okay, iron 2 plus, where to go? And so that would be 0.45, believe. And then let's compare it to magnesium, but you guys were already suspicious since it's lower. And so, yes, this would be a negative 2.37 volt process there. And so when we add those together, so 0.45 plus negative 2.37, and so we do get a negative number, so negative 1.92. Could have slight discrepancies depending on when you're getting your value. But yeah, so to your point, so I like that you did it by the kind of seeing what metal is lower method, so that's good. But again, right, you can add up your half reactions, see that it's negative, so then non-spontaneous, at least in the direction that it's written, right? So we could totally flip this reaction and then, okay, well, as long as our magnesium then is supplying the electrons, right, then this process should be spontaneous. So really, the magnesium needs to be the anode. Good. So what about B? What did we find? Spontaneous, non-spontaneous? So spontaneous. So did we do our trick again, maybe? So we find, so where's our iron versus lead? So now iron is lower. So it should be our anode. But again, I like to write out our numbers just to verify before I get squirrely. So positive 4.5 volts again for iron. And then let's look at lead, 2 plus, going to lead. And so that is negative 0.13 volts. And so even though it's slightly negative, right, still overall positive. So 0.45 plus negative 0.13. And it's about 32 volts for our potential. Or 0.32, sorry, 0.32 volts for our E cell there. And then probably in our last few minutes of class, so now practice drawing out B, the little cell diagram. So draw B. Maybe if you have time, how would you fix A to be spontaneous? So at least draw B out, kind of sketch it out. So then, as we just finish up, right, double check your drawing. So I'm basing it off of B. Again, iron is our anode. And maybe you want to label that just for your own sanity. And then, right, we can use iron metal. That's appropriate, right? That's part of our reaction. Iron solid, so good. That can be our little electrode there. Iron 2 plus species running around in solution. Then electrons, right, drawing our flow. And there's my oversimplified light bulb. Then continuing electrons. And then again, we can use our lead metal piece that's appropriate, dipped in our solution of lead 2 plus ions, probably a nitrate for solubility. And then don't forget your salt bridge, of course. So you can just label it salt bridge, and then you don't have to add in the ions. I'm just kind of doing it to be cute. So it doesn't matter what our ions are, just as long as we have some sort of activity flow. And maybe we'll label this cathode. And so that looks good. And so if we wanted to, right, we could kind of redraw A. And so we could fix A. And so all that means is magnesium, right, has to be our anode. And so now the electrons will flow in the appropriate direction. And then iron can serve as our cathode then in our iron 2 plus solution, and again, salt bridge to complete your circuit. And maybe practice to your shorthand if you need to, write magnesium, magnesium 2 plus, double bridge, Fe2 plus, Fe, and I'll write the top one up here too. So metal, ion solution, double line, next metal, with, again, the outer parts containing your solid metal electrode to kind of help you. All right, we'll stop here today. We'll continue on. So I think we'll finally get to delta G. I know you guys are so excited about more Gibbs again. So we'll look at our formulas that relate everything together on Thursday. And we'll keep calculating our cell potentials and then relating them to G and probably some K. All right, lab should be fun. Oh, sounds like the picture crew is canceling on us on the last minute this week, so for better or for worse for people. So I'll see everybody in lab for the one-pot reactions. The one-pot is still on. Let me know if you have questions. Then field trip next Tuesday. I'll keep streaming for a few minutes in case there are questions. Make sure you get your exam back. If you didn't take the exam, take it ASAP. I think I've sent copies to the testing centers, but you can bug me.